Okay, let's solve another problem. Now, what we just discussed is a one block as the system. What if we have two blocks, or we say more than one particle? So we have a table, and we have a spring constant K, and it's connected to a block of mass M. There's no friction between mass M and the tabletop. And then there's a pulley, and there's a string, rigid string, and we have a block right here. Let's say 4 times of that. So obviously that because this one is heavier than the other one, as a matter of fact, this one's mass, we should say weight, is balanced by normal force. So as a matter of fact, it doesn't matter what mass is this one. We have a mass hanging here, and the object will start to fall. Let's say we let it fall by a distance h. And obviously, because initially the system is M and 4M both are at rest, and spring is at its original length, no stretch or no compression. So the object has no speed. And then when the object starts to fall, there must be an acceleration. How much this one fall and how much this one will go to the right, because we have a rigid string right here. So that means that the distance between M and 4M is fixed. So how much 4M drops down, and then how much M has to move to the right. So the question is, since both blocks, first of all, travel the same distance, they start from initial speed equals 0, therefore they must have the same rate of acceleration because they travel the same distance. So at that moment, they must have the same speed. Again, we talk about speed because the velocity is different. This one moves to the right, this one moves down. The question is, what is the speed of both blocks if we let the 4M drops by distance h? So we have to say, define our system. Define our system as M plus 4M. And also we have to look at when the 4M start to drop, when this M move to the right, how many forces are on them. We already draw this 2, but when the M move to the right, we should add one more, which is the Kx force, which is elastic force. And actually, there is the tension here. Theoretically, if we do not consider friction between the string and the pulley, this is the pulley, P, and then this tension on the 4M we can consider as a action-reaction force with the tension on the M. Well, since there's no friction between the string and the pulley, tension T is not frictional. So the internal force here is not frictional. It is very important that when we apply that sigma W non-conductive equals to delta of ME, that equation. Now, as a matter of fact, if we only have one object, then there's no problem. But if we define that 2 objects as our system, then here is the work done by external non-conductive force. So we have to guarantee that, because in this equation internal force does not show up since we define M plus 4M as the system. So when that happens, we have to make sure that our internal forces are non-frictional. Because if internal, for example, if the work done by external non-conductive force equal to 0, then we say, oh, mechanical energy is conserved because delta M equal to 0. However, if our internal is frictional, it's going to cost our energy, mechanical energy. So mechanical energy will get lost. So we cannot say system mechanical energy is conserved. So we have to make sure that internal is non-frictional. So we have two more forces to, actually here is 4mg, this is the one, and we have 1, 2, 3, 4, 5, 6. But if we count external, the external will be the 4mg, 1mg, the Fn, the kx, and this is a pair of internal forces. So look at all the external forces, and it is only Fn is non-conductive, and since our displacement is perpendicular to Fn, and we say that our conclusion, sigma of Wnc equals to work done by normal force equals to 0, and our mechanical energy is conserved since our internal is non-frictional. And we're going to use the change of mechanical energy, that idea again, that 1/2 of system is m plus 4m, that's 5m, mass v square minus 0, that is change of kinetic energy because initial both are at rest, plus change of elastic potential, that will be 1/2 k of h square minus 0 because initially the spring is not being stretched, and when 4m drops by h, m moved to the right by h, spring has been stretched by h. And as far as for gravitational potential energy, be careful, we're talking about our system. So this part of system, gravitational potential energy does not change, but that part, yes, it dropped. So it's negative 4mg of h. So change of kinetic, change of elastic, change of gravitational, that equals to 0. So this is delta Ke, delta U of epsilon, delta U of G. And from here, and we can answer the question, let 4m drop by h, and what is the speed of both blocks? Now, let's add a what if. What if there is a mu k between the block M and table? Then we need to add one more force, that Fk. So in that case, we have a Fk as a non-conductive force does negative work because the block moved to the right by h, and Fk is to the left. That equals to our change of, that is 1/2 of 5m of v, this time I use the v as v prime square, and that's the change of kinetic, and elastic potential 1/2 k h square minus 0, that's the change, and gravitational negative 4mg of h. We redefine the question. If there is kinetic friction between block M and table, we let 4m drop by h. By then, what is the speed of both blocks? So we can use this equation to solve. We still need to figure out Fk. Again, Fk defined as mu k times normal force. For the block on the table, normal force in this case exactly equals to mg because the vertical directions there's only two forces. So therefore we have this mu k. Fn can be replaced by mg. So we know our Fk, we can plug in here and we can solve for a v prime. Let's continue on this example 2 problem, and we just remember that in our case we define m2 equals to 4 times of m1. Remember, this is m, that's 4m, so that is that. And the string is rigid, and there's no friction, rigid, non-frictional right here. And now let's ask this question. What will be the maximum stretch to the spring if we let M2 drop? So what happened is, let's look at what happened. That M1G is balanced by Fn. And for the M2, M2G will be bigger than the tension T. So M2 will start to accelerate down. And since M1, M2 have to travel the same distance, then M1 has to accelerate at the same rate to the right, and spring will be stretched. Once the spring being stretched, the spring wants to pull the block M1 back. There is a Kx force. But at the very beginning, that the acceleration is large. So this M2 will continue to speed up down, and this one do to the right. But with the bigger and bigger the stretch to the spring, Kx force start to gain hand. It get bigger and bigger. So eventually you can imagine that the both block will start to, the acceleration will get smaller and smaller until that both of them stops. When both of them stops, X will be the maximum stretch, because next moment the Kx force will pull M1 back, and then M2 will go up. So this will actually behave a kind of like oscillation back and forth. So knowing so that we're going to use this sigma of W non-conservative equals to delta ME, and also we define our system as that M1 plus M2. By doing so, that the non-conservative force in this case is Fn alone, so work done by this non-conservative force sigma end up is work done by Fn alone equal to 0. So our mechanical energy change is 0. That means mechanical energy is conserved. When we think about the maximum X, which is the maximum stretch, both blocks stops, because if both blocks continue to move, spring will be stretched more. So our kinetic energy change is final 0, initial 0, because starting with rest and with maximum stretch, they stop again. So 0 minus 0. And that time, potential energy is 1/2 Kx max of square minus 0, because initially is no stretch. And the gravitational potential energy, M1 is still on the tabletop, there's no change, but M2 dropped. Minus of M2 G of X max. That is the change of kinetic, change of gravitational, change of elastic potential, change of gravitational potential. From there, we can solve what is the maximum stretch to the spring.